Let's talk about waves today. Now I have this system here. It's a bunch of tape, and on it I've got these little skewers with pom-poms in the end. And if I tweak it at this end, I get a wave that travels down the medium. And if you look, the pom-poms are moving up and down, but the wave is moving side to side. Looking at the motion of the pom-poms, that's a transverse wave. The pom-poms are moving this way, the wave is moving that way. But we can have a wave where the wave is moving this way, but the motion of the particles that carry the wave is going this way. There's a difference between the motion of the wave and the motion of the medium. We can have these so-called transverse waves where the motion of the medium is one way and the wave is another, or longitudinal waves where they're along the same axis. Now, when you have an earthquake wave, it works like this. A tremendous disturbance in the Earth's crust sends out waves to the Earth's crust. You don't like to think about the Earth as being flexible enough to carry waves, but it is. It sends out a wave. And when you feel an earthquake at some distance from the epicenter, what you're feeling is the waves that have traveled outward from that source. And there's two different kinds of waves. There's transverse waves, where the motion is perpendicular to the motion of the wave, and longitudinal waves, where it's parallel to the motion of the wave. Those are the so-called S waves and the P waves. And you can sense them some distance from the source. Let's look at a problem concerning waves in the Earth, earthquake waves. Okay, here's the problem. A 1994 earthquake in Southern California produced measurable up-down motion of the ground 375 kilometers away at a station in Santa Cruz that began 1 minute and 40 seconds after the quake. A seismometer showed essentially sinusoidal motion of the ground with 6 complete cycles taking 20 seconds, with a maximum speed of 1.5 millimeters per second. We have a couple questions. Was this a transverse or a longitudinal earthquake wave? What was the wavelength? And what was the total range, top to bottom, of the vertical motion? Let's look at these in turn. We're going to start by asking you to answer the first piece. Was this a transverse or a longitudinal earthquake wave? Let's look at the choices. Let's draw a picture, and we're going to draw a side view of the motion. We have an earthquake wave that was traveling from Southern California to Northern California. So it's heading towards the north. The ground is moving up and down. And so the motion of the ground is perpendicular to the actual motion of the wave. So it's a transverse wave. And transverse earthquake waves are known as S waves. They get there second. The P wave, the compression wave, got there first. And the P wave made motion along this axis, along the same axis as the travel of the earthquake wave. But the answer to our question is this: it's a transverse wave. Now, let's do the rest of the problem. Let's go back and look at the problem statement again. Here's the data that we need. The earthquake was measured 375 kilometers away from where it first began. And that was 1 minute and 40 seconds after the quake. And if we looked at the motion of the ground, it made 6 complete cycles in 20 seconds. And there was a maximum speed of 1.5 millimeters per second. Those are the pieces of information that we have. Let's look at what we need to answer. First off, what was the wavelength of the wave? Now, if we look at the data we're given for the wave, here's what we're told. We're told 6 complete cycles took 20 seconds. We can use that information to calculate the frequency of the wave. Because think about it, 6 cycles of the wave. If I drew a picture of a graph of the wave, and if I look at the vertical motion as a function of time, 6 cycles of the wave took 20 seconds. Frequency is just cycles per second. So the frequency of the wave is just this: 6 cycles, 20 seconds. So the frequency, 0.3 hertz. That's the frequency of our wave. But we weren't asked for the frequency. We were asked to find the wavelength of the wave. And in order to do that, we need an additional piece of information. And what is it? We'll give you some choices. Our fundamental relationship for sinusoidal waves is this: the velocity of a wave is equal to the frequency times the wavelength. So if we know the frequency, we can calculate the wavelength. The wavelength is just equal to the velocity divided by the frequency. So to finish this problem, to compute the wavelength, we need to know the velocity of the wave. And we know that because we were told that the wave traveled a distance of 375 kilometers, or 375,000 meters, in a time of 1 minute and 40 seconds, or 100 seconds. So the speed of the wave, 3,750 meters per second. So if we know the speed of the wave and we know the frequency of the wave, we can calculate the wavelength. The wavelength is equal to the speed, 3,750 meters per second, divided by the frequency, 0.3 cycles per second, so seconds to the minus 1. And if we work that out, we get a wavelength of about 12,000 meters, or 12 kilometers. That's our final answer for the wavelength. That's big, but that's typical for earthquakes. That's not at all unusual. The speed is high too, 3,750 meters per second. That's a typical speed for earthquake waves. They can go a little bit higher, they can go a little bit lower, but that's a typical speed. So far, so good. But of course, the things that people are really concerned with earthquakes is the fact that they shake the ground. That takes us back to the question of the motion of the medium. Okay, think about it. We said the wave is traveling this way. The ground is moving up and down. It's a sinusoidal wave, we were told that. So if I look at the motion of the ground, if I look at the up and down motion, it is simple harmonic motion. And because it's simple harmonic motion, we can use the equations of simple harmonic motion to solve for it. And we have a couple. But we were just told we wanted to find the total range top to bottom of the vertical motion. Now if we plot the motion of the ground as a function of time, it's a sinusoidal oscillation. We were told that. There's a couple of properties of the wave. One is the period or the frequency. Okay, and we know that. We know the period of the wave because we know the frequency. But another thing that characterizes it is the amplitude. But we weren't asked to find the amplitude. We were asked to find the total range top to bottom of the vertical motion. And if I have this wave coming by and the ground is moving like this, what is the total range top to bottom of the vertical motion? I'll give you some choices. The ground moves up and down with this sinusoidal oscillation. The amplitude is how far it moves from its equilibrium position. So it moves from the equilibrium position to a height of A above the equilibrium position and to a height of A below the equilibrium position. The total travel, top to bottom, the total range of motion is actually 2 times the amplitude of the wave. So if we solve for the amplitude of the wave, we can solve for the total motion that we have here. Now, how do we get the amplitude? Well, another piece of the puzzle we were given was this. We were told that the maximum speed was 1.5 meters per second. And it turns out that's what seismometers usually record. They usually record the speed of the ground, not the motion of the ground. And the maximum vertical speed of the ground, 1.5 millimeters per second. But we need to put that in meters per second in order to be able to use this. So in meters per second, it's 0.0015 meters per second. That's my maximum speed. Now remember, if I have simple harmonic motion, so think back to your simple harmonic motion relationships, the maximum speed was just equal to 2 pi times the frequency of the wave times the amplitude. What we're trying to solve for in this problem is the amplitude, and the amplitude is just equal to the maximum speed divided by 2 pi times the frequency. And we know the frequency, that's 0.3. We know the maximum speed, 0.0015 meters per second. And so if we work it out, we get an amplitude of 0.00080 meters. That's my amplitude. So the total motion of the ground, top to bottom, that's 2 times the amplitude. It's double that, 0.0016 meters, or 1.6 millimeters. And that's our final result. Now let's take a look and see if that makes sense. You probably don't have a lot of practical experience with earthquake waves, so to make sense of the result, we're going to take a look at some online information about earthquake waves. We already said the number that we calculated for the speed is a typical value for earthquake waves. They vary between about 3 and 8 kilometers per second. We found about 3.7 kilometers per second, so our number is quite reasonable. Also, too, this was an earthquake in 1994, and we were talking about the motion of the ground in Santa Cruz. That's at some distance from the earthquake. Well, the earthquake occurred in Southern California, where they have earthquakes pretty regularly. It was detected further north in California. And you don't think of Santa Cruz as being a place that feels a lot of earthquakes, and it isn't. The waves go through there, but by the time they get there, they've died down in amplitude, enough that you can detect them, but not enough that it's creating tremendous disturbances. So we didn't hear about Santa Cruz being shaken in 1994. So we expect the result for the motion of the ground to be pretty small. And it is 1.6 millimeters top to bottom. So it's a very, very tiny displacement of the ground. You might be able to feel it when that passes, but it wouldn't cause damage. And if you look at the numbers that we found are actually quite reasonable for a typical earthquake. And in fact, if you were in Santa Cruz when that wave passed, you might have noticed it, but not much would have happened. And that's exactly what we find if we look. Not a huge surprise. Physics is about the world around us.